What is 6G all about? You can't go to an advanced wireless symposium without seeing the International Telecommunications Union's 5G triangle. Well, we're not going to talk about that today. I imagine you're going to see that from somebody, if not me, today, but that is not going to be my topic. 6G actually now has a new spider diagram from the ITU to describe how much more advancements are going to have to be made in the various KPIs for network performance. We're not going to talk about that either. And in fact, there's a reverse spider diagram that compares all of the KPIs with the amount of demand each one of the use cases will have on that KPI. It's a very informative graphic. We're not going to talk about that either. I'm a test and measurement guy. I come from a company that does measurement and validation, and that is what I'm going to talk about today, because that's what 6G means to me in the business that we're in. And that's the perspective that I think I can provide for you all that is somewhat unique. First, a little bit of history. Now, I'm not physically there, and I can't ask you to raise your hands or respond to this. Otherwise, I would have said, does anybody know the significance of this date, 1979? I'm sure there are some of you who will raise your hands and say that is when NTT launched the first automated mobile phone service. Now, automated means that the connection of the mobile call did not have to be done through an operator, and the handovers from cell to cell were automatic, and frequency reuse was significant. This was launched in Tokyo in 1979. A couple years later, Nordic Mobile Telephone was launched by this newly formed company called Mobira that was a joint venture between Nokia and one other company, and that was launched in Sweden. And then a few years later, we saw AMPS being launched in the United States by AT&T. All of these were analog systems. You'll notice that my timeline goes back in time. Well, we are barely into 2020 here, and we're already talking about 6G, something that is already called IMT 2030 or Network 2030, and won't become mainstream probably until 2035. What are we doing talking about that now in 2020? We're doing that because it takes time. These technologies take time to evolve, and we have to evolve the solutions, and we in the test and measurement world have to evolve the test and measurement. I went and looked and found that the first NMT standards meeting was in 1970, 11 years before the NMT launched. So it takes time to develop the standard and to refine the technology to make these new systems work. And you can see the same in the test and measurement world. This is the 8955 transceiver test system that was developed by Hewlett-Packard and launched shortly before I started working for HP in 1985. And it's a big system, multiple general purpose boxes configured together for what is required for making measurements on transceivers, and then that 8965 interface box featured down there in the lower right, which would customize the system depending on the particular type of transceiver standard. We had an AMPS version, we had an NMT version, and so forth. And it's a very nice, easy to use system, but it's big and complex and expensive. Not too long after that, we were able to, for the sake of mobile phone testing, replace that entire thing with, in this case, the HP 8920A, launched in 1989, which is something you could actually carry around. And that's what happens over time. You start with large prototype systems. Technology allows you to refine, miniaturize, make them more compact, make them more of a point solution, and in the case of the 8920, a very efficient way of making the measurements that were necessary, in this case, on mobile phones. So what does that history look like for the previous generations? Well, I might be exaggerating a little bit to suggest that 1G started in the 1940s, but that is about the time, 1947, when the folks at Bell Labs and AT&T came up with the idea of the hexagonal cell. for the sake of frequency use and making what they called at the time small cells, so that we could have much more efficient use of spectrum. Now, that took a long time to become manifest as cellular telephones in the late 1970s, early 1980s. So maybe it's a bit exaggeration to say it went back to 1947, but it does take time to invent these things, and things evolve during the course of that invention. In the case of GSM, the first GSM meeting, the consortium that formed the Memorandum of Understanding to develop the standard, met in 1982 for a launch in 1991. You can see with the other generations, somewhere between 10 and 15 years between inception and launch. It depends a little bit about how soon the system actually started, whether that was forming the vision in ITU or starting the standards discussion. But it does take time to do this, and it takes a very interesting path in terms of evolution. If we look at the way the standards evolved and the systems evolved over time, you can see here, starting early on in 1G, the ability simply to carry your mobile phone around, maybe just within your country. NMT actually did roam between a few countries, but for the most part, this was country specific. And I found a very entertaining video that was put together by AT&T for the sake of AMPS, I think in 1978. This is out there on the internet, and I will send a link to those of you who request. That is AT&T advertising this AMPS technology and showing how much more convenient it will be when you no longer have to stop your car and get out of your car to find a payphone to make a phone call. And you can make that phone call while you're on the move. So that evolves then into digital communications, which became a global standard and was enabled us to roam internationally with an international standard of GSM. Evolving then into 3G and 4G with the mobile internet, and with 5G, which is now becoming manifest in its early phase, which is a connection to the system from anywhere, and multiple connections, multiple types of connections and use models, and that evolving to 6G, which is a human to the system interaction and a machine to machine interaction in even more different ways, which are only now being put together as part of the vision. And that's a transition over the past, in this case, 5 decades, well, starting in 2030, over the past 5 decades, of carrying my phone anywhere to carrying my office anywhere to mobile communications being integral to society. And that's a key part of the message that I want to get across today, is how important this is going to be for the sake of society, and how that in fact impacts what we do from the standpoint of test and measurement. Within Keysight, and to a large extent in the industry itself, in the early days of 1G, we were very much focused on making physical measurements on the physics of what's going on. RF power, modulation accuracy, occupied bandwidth, how good of a neighbor am I, sensitivity, how good is my receiver, or adjacent channel rejection issues, how well do I tolerate bad neighbors. Very focused on the radio, how well is this system going to operate in a mobile environment. Now, all of that stuff had to be measured and thought about, and became actually more complex in 2G, but we added things related to digital modulation, bit error rate, power versus time, necessary steps to see how well this system is going to work. And I think some of you will remember also how important it became for us to measure the quality of voice codecs because of their impact on voice and how understandable somebody would be. That was a big deal back in the 2G days. Well, once again, all of that still has to be measured, and actually I make the words smaller, but this ends up being more complex as we move forward in generations. But we add things in every generation. In this case, we had the code domain for wideband CDMA and code division multiple access capabilities. No longer worried about just bit error rate, but block error rate. How well is my message getting across, not just individual bits? So it's more advanced in terms of measuring the capability of the system, the quality of the receiver. Also, how cellular, or how the cells themselves would behave. I think some of you might have remembered in the early days of CDMA where the cells would breathe and they would grow and shrink in size based on some issues with the initial system designs, making sure that antennas and rake receivers worked properly. And all of that still has to be done in the new systems, but now we add, for the sake of 4G, how does the scheduler work? We have much more complicated modulation systems. So what does that constellation diagram actually look like? We're now making a lot of measurements over the air. There are measurements on how well we're getting packets and packet flow from one place to the other. And for the first time, we're really looking seriously at quality of service measurements and keeping that in mind for how well our system is operating. As we move into 5G, all of that has to be done, but we're now also having to consider new issues. The 5G threat surface is much broader than 4G, and so security becomes a major issue. From the very early days of 5G, we've been talking about latency and reliability, and now we have to measure those. How reliable is the system? How do you quantify that? How good is your latency? How do you quantify that? And also, how efficient is the network in terms of power use, in terms of spectrum use, and how well your schedulers are working and so forth. All of that has to be considered in 5G. And in 6G, all of that has to be done, but I maintain we're going to start to add the requirements for measurements to be more driven by policy. Not just like what the FCC or CEPT dictates in terms of power levels, EMF exposure, and that sort of thing, but are you living up to your service level agreement? We're looking at systems where operators will be selling services to governments, to other businesses, to consumers, and they will have to live up to a certain level of service. How do they measure that? How do you ensure that this is going to behave the way it's supposed to? Particularly when we add not just systems that have to arrive and data that has to arrive in time, but also on time, where latency no longer has just a minimum requirement, but also a maximum requirement, or vice versa. So, and then we would also potentially add numbers to quality of experience. This is something I've seen in over the past several decades, but it is very difficult to measure in a consistent manner, and I think we're going to see more of that, and that will be in the context of policy. So we have moved from a lot of focus in my own company as well, from making measurements on the physics, on the physical part of what's going on in the radios and the underlying electronics, to how well is the data system performing, how well is the system performing, and then ultimately how well is it performing as a part of society. This is perhaps evidenced even better with this slide that has a lot of words on it, but it is indicative of the kinds of questions that we are getting as a company now that we're involved in making measurements not just at the physical layer, but also at higher layers in the protocol stack, as well as all the way up to the application layer, and that includes security-related items. All of these items here are related to how well is the system working overall, not just the physics. Every one of these, or at least some of them, can be related to what's going on at the physical layer, but it's a much more complex system with a much higher amount of societal demand, and these kinds of questions become more and more complex as time goes on, and in some cases at a higher level of abstraction and even more difficult to quantify. So what does that mean for 6G, for us in Keysight, and for you as you develop this and need to make measurements on the systems? Well, starting with just getting very, very high data rates, 1 terabit per second per user, for example, this is laid out as a KPI. Well, many of you in this symposium right now are focused on terahertz or sub-terahertz radio systems. Much wider bandwidths, much higher frequencies, higher data rates, the movement of bits around inside of systems much, much faster, the transport of bits between one system and another much, much faster. A lot of that still is, how do the physics of the system work? How can you measure the physical attributes of what's going on? But not just that, we're now going to have much more complex radio systems, not just like we have now, 4G and 5G working together in, for example, a non-standalone system, but maybe as 6G comes on board, it'll be 4G, 5G, and 6G, plus Wi-Fi, Bluetooth, near-field communications, maybe some of the IoT systems, all interacting in as seamless a manner as possible, and all hopefully not interfering with each other as seamlessly as possible, so that your complex radio system behaves the way it should. And this is a system level of functionality, something that we need to help you measure as well. But you get to a higher level, ultimately what matters is how well does a network operate for the service that we expect it to provide, the end-to-end design and validation and optimization of the network. What is that quality of service based on the service you've defined and sold to your customer base, based on the expectation that's been set, and whether that's built into a service level agreement or potentially even a policy agreement with a local government, and add to that quality of experience, which will become a higher and higher expectation. And I've already mentioned security as one of the most significant issues that we will have to work on, and we will have to measure that. How good is the security? How well do you prevent intrusion? How well do you react when it is successful? Do you know whether or not an intrusion worked? All those things will need to be measured. So we started with the physical measurements. We're moving to much more complex system interaction to ensure that behaves properly, that we can put a quantifiable number on that. And then, how well does the system interact with society? So I speak about many of these things, and my call to action is what a lot of you are doing right now, right here in the symposium. And again, I wish I was there with you. First of all, learn everything you can. There's a lot of questions you can ask. I certainly ask plenty. I have to admit that I start with Wikipedia. It's not always the greatest source of information, but it's a good way of discovering what you don't know. Most of you are already reading research papers, and you, of course, are doing research on this. But also you need to do that knowing what happens in the current system. How does the current system work? What's good, what's bad, and where are the standards headed with respect to the next step in 4G and 5G. And then, obviously, we all have to explore these new enabling underlying technologies and their interactions. This is all part of making these new systems work, whether that's new software technology, work in quantum and quantum computing, new semiconductor technologies. And all of that has to be done like what's happening now in the room that you're in right now listening to me, which is partnering with the experts and the leaders, whether that's academia, people in the commercial space, consortia that are working together, or governments. And I will highlight once again that government situation. Everything we do is done in the context of policy, and governments are under a lot of pressure in wireless communications to set policies that make sense for society. And you see this all over the place. I bring this up quite a bit, and even in my own company, sometimes people roll their eyes and say, well, that's not going to be dictated by policy. And I will challenge you that perhaps it will. Let's go back in history again. Does anybody know what this is? Well, of course you can't answer me on a real-time basis because I'm not really there. But this is the Morse code for SOS. This is an international agreed approach to identifying that I am in distress and I need some help. SOS was not always the standard for a distress call. In fact, it was not an international standard until 1906, when this body got together and decided SOS was going to be the case. It turns out SOS does not stand for anything. It is just one of the more easy Morse codes to understand and not get mixed up with something else. 3 dots, followed by 3 dashes, followed by 3 dots. But that's not where this ended. In the next decade and a half after this was set as a standard, this body also met to agree that distress signals in wireless telegraph would be communicated on a specific frequency, that is 500 kilohertz. That was important so that you always knew that if a signal was going to come in that was distress, it was going to come in on that band. Not only that, in the wake of the sinking of the Titanic, they insisted as a matter of international maritime law that telegraph offices inside of ocean-going vessels were to be manned 24 hours a day, 7 days a week, no matter what. And that is in the wake of a missed opportunity when the Titanic sank. So not only do we have a code that is standardized by a body and then dictated by international maritime law, but we also have a frequency and a set of behaviors, notably making sure that you have someone in that office all of the time. This has been going on for 100 years with a long list of other changes in how wireless communications and wireline communications policy is set. And we take for granted not just what some of those laws are and the technical nature of them, but also some of the behavior around that is required. And that's not going to stop. And we're going to be confronted with that in a very large extent with respect to 6G as wireless goes from a novelty to a fundamental requirement for societal behavior.